All right, let's wrap it up. So, you guys can ask me more questions about this next time we meet if you'd like, but I just wanted to give you a brief rundown of power series, multivariate power series. So first of all, here's the Taylor expansion in Calculus 1. Okay, fine, 2. Should be in Calculus 1. Anyway, whatever. If you do two variable, you can derive this. It's derived in my notes. It's pretty simple to do such, but this is what you get. You get, well, the piece we've already talked about, linearization, but then the next piece up, you get something that is a quadratic form. And so this quadratic form is sometimes called the Hessian. You factor out a half to keep things pretty. So there's the Hessian matrix. It's the matrix of second derivatives, which by the way is symmetric because partial derivatives commute. If you have three variables, all right, three variables looks like this. So we got these first two pieces, which is the linearization we already talked about. And then for three variables, you have a 3 by 3 matrix of second derivatives, which again we call the Hessian matrix. These are equal. I don't know why I wrote them like that. But there you go. This would be the Hessian matrix in 3 by 3 case, the function 3 variables. And then of course if you can do it for 1, do it for 2, you can do it for 3, you might as well do it for n. So for n variables, we have the linearization, and then this is always for a real valued function. I suppose you could look at the vector valued function and look at like component expansions, but I don't see the need at the moment. And anyway, so there's the linearization, and then this would be the Hessian piece, which again is a second derivative matrix sandwiched between these difference vectors. Again, this gives a quadratic form, all right? And by construction, that's symmetric, which means we can apply that eigenvalue stuff to it, right? So this is the Hessian matrix of F. Let me show you an example or two. Really beautiful stuff. And so essentially, you can use the series you already know from Calculus 2 to make neat examples. Like this is x times the geometric series, right? 1 over 1 minus y is x times 1 plus y squared plus da 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 da, right? So I can multiply that out. I get this. Now, this is centered at 0, 0. I mean, you could center it somewhere else. Maybe I'll do some of that next time if you guys ask me nice. And I'm awake. But at the origin, the matrix is just got that one term, just 1/2, 0, 0. But that's about as far as I go. I mean, when we're trying to think about, one of the things we're after here is how to minimize or maximize a function over some like bounded region. So on the edge of the bounded region, we could use the method of Lagrange multipliers to look for extrema on the constraint of the boundary. We could define by some sort of constraint, right? On the interior, we expect that wherever there's a minimum or a maximum, a local extreme, if you will, that would be a place where the gradient 0. So here 0, 0 is not a critical point. It's not a place where the gradient is 0 because, well, you can see from this that it had a partial derivative of f with respect to x at 0 of being 1. So it's not critical, so I won't even say more about that there. Now the next example, f of x, y, z, x squared, sine y, z. Now most of my examples don't actually have any differentiation. I'm just straight up stealing from Calculus 2 and theorems I haven't proved, namely that like there's like these compositive series theorems where you can build series in several variables from a series that you know in one variable composed with functions of several variables, provided certain conditions. I think there's proofs of some of those things in Edwards, but if you ask me for a better source, I'd have to look. Anyway, so here it is. Of course, e to the x squared expands like so, and sine yz by substitution is theta minus 1 over 3 factorial theta cubed plus 1 over 5 factorial theta to the 5th plus da da da, where theta is yz. So if I collect lowest order terms, I get like quadratic of yz. I get this 6th order term, and then I get a 4th order term. Like, oh no, oops. Like, it's a matter of common human decency to write it lowest to highest. So this plus this is wrong. I should really write it like this: 2nd order, 4th order, and here's all your 6th order terms, I think. I was like, oh no, it's 5th order, but I'm wrong. That's 10th order. Yowzers. Anyway, this time you notice that there are no linear terms, which speaks to the fact that the gradient at 0 is 0. So 0, 0, 0 is a critical point, and so we can ask ourselves the question: what kind of critical point is it? Is it a local min? Is it a local max? Is it neither? How can we decide? And so it's tough here to decide because it's got this mixed term yz. But here's how to be sure that it is in fact a saddle. Here's how to think about that. So I calculate the quadratic, the Hessian matrix, which is this, and then I calculate its eigenvalues. And this little calculation here shows me the eigenvalues are 0, 1/2, and -1/2. I put them in the wrong order. Here, I put them back in order. -1/2, then 0, then 1/2. And so if you think about it, f of 0, 0 is neither max nor min, because what would the formula for f of x, y, z look like near 0, 0, 0? It'd be like -1/2 eigenvalue coordinate squared plus 1/2 eigenvalue coordinate squared plus higher order terms in x1 bar, x2 bar, and x3 bar. I'm using x1 bar and x2 bar and x3 bar for eigencoordinates, all right, which were the ones I alluded to in the last little video. So if you think about that, if you go in one direction, it's increasing. If you go in another direction, it's decreasing, right? And so we can tell it's a saddle. That's the argument. I'll get back to example 3. Example 2.5. Just to, remind you guys, if we have functions like this, x squared plus y squared minus z squared, or if I have f of x1, x2, xn, and it's equal to x1 squared plus 2x2 squared plus 3x3 squared plus nxn squared. Like, I don't need sophisticated calculus to tell you about mins and maxes here. It's easy enough to see that the gradient of f at 0 is 0, and the gradient of f at 0 is 0, right? So 0 is a critical point. And I can tell just from looking at this that it is a saddle, because you notice if I change, if I keep x and y 0 and I go along the z direction, I'm going to be decreasing, right? But if I fix z to be 0 and I go along the x and y direction away from the origin, I'm increasing. So some directions I'm increasing, some directions I'm decreasing, which means that f of 0, 0, 0, 0, 0, 0 is a saddle point. On the other hand, this one here, it doesn't matter which way I go away from the origin, I'm increasing, right? Because it's the sum of squares. So this is the point. If we look at the eigencoordinates for the Hessian, it reveals to us the formula in terms of a sum of squares. And from that sum of squares formula, you can directly see whether or not it's a minimum or maximum or a saddle. And that's it in a nutshell. Just to clean up, just one last thing, and then I'll really shut up for today. So in calculus 3, of course, we have that second derivative test, and it's not that bad to derive it from what we have. This is our multivariate Taylor expansion, all right, which again I can derive from the single variate Taylor and chain rule. I haven't done that today, but it could be done. Maybe I'll do it next time if you guys ask me nicely. And I started trying to calculate the eigenvalues for this, but it can be done. This is not the fast way to do it. There's an easier way. So for a 2x2 matrix, super nice result is that the trace is the sum of the eigenvalues and the determinant's the product of the eigenvalues. Actually, this is true for an n by n matrix, but it's especially useful for a 2x2 matrix in this one because the trace of the Hessian is the sum of the second derivatives, but the determinant of the Hessian is this thing. Now, that's what we call D from calculus 3, right? Now think about it. That D is going to be the product of the eigenvalues. So if they're both positive, that would be a local, that would be something like, here, let me just demystify it here. Z equals to x squared plus y squared, versus z equal to minus x squared minus y squared. One of those is a paraboloid which opens up. One of those is a paraboloid, right, which opens what? Down, right? So maximum, minimum. Both positive, minimum. Both negative, maximum. But either maximum or minimum, the product of positive positive or negative negative gives me positive. So this D from calculus 3, evaluated at the critical point, had better be positive if it's actually going to be a local max or min. On the other hand, if it's not a local max or min, if we have one is negative and one is positive, and then the product of a positive and negative is going to be negative, so you can easily see that D less than 0 corresponds to the case that we have distinct eigenvalues, and consequently, in the right coordinate system, it looks like a saddle. Now this actually gives you a path towards finding the coordinate system, which makes the graph look like a saddle, at least local to the critical point. Now if one of the eigenvalues is 0, then this breaks down, because there could be contributions from the higher order than the Hessian piece in the expansion, and so further analysis is required. But that's it in a nutshell. You can use the theory of quadratic forms and eigenvectors and eigenvalues to clearly understand, what the Hessian piece looks like for a multivariate expansion, and so you can figure out mins and maxes from that viewpoint. Unfortunately, there's nothing so simple as this for the third order case. Like the third order case really requires linear algebra in general, which is why we don't teach it in calculus 3. But for calculus 3, this fortunate simplification happens, so we can present a second derivative test. The second derivative test for 3 or 4 or 5 variables is much, much more complicated, and it involves the full weight of linear algebra. Anyway, I shall shut up, and I hope you guys enjoyed it.